So hello and welcome back to Aayu Pathshala. And today we are going to start with the EDC, and we will limit ourselves to the previous question that has been asked on this topic, and we will see some topic around it. So this is my channel Aayu Pathshala, and wherein I have created a dedicated playlist named as DCIO Preparation 2025. So subscribe to it and check it out that playlist. There are different videos on different topics such as the computer organizations, operating systems, data structures. So you can also check that out if required. And this is the Telegram channel wherein the materials related to this is being uploaded. So let us start with the first question wherein it has been asked that consider the following statement regarding the motion of charged particle in magnetic field. The first one is a particle whose initial velocity has no component normal to the uniform magnetic field will continue to move with a constant speed along the line of flux. See, this question has been asked from the concept of Lorentz force. What is it? See, when a charged particle is moving in a magnetic field, the force acting on it is given by Q, where Q is the charged particle, V is the velocity, cross with B, where B is the magnetic field. So, obviously, we know that the cross product is given by VB sine theta. And when theta is equal to 0, that is when the particle is moving parallel to the magnetic field, then the Lorentz force acting on it is become 0. So here in the question, it has been given that the component has no component normal to the uniform magnetic field. So that means there is no component normal to magnetic field. That means V cross B will be equal to 0. If V cross B is equal to 0, we can say F is equal to 0. If F is equal to 0 on that particle, so the particle on which no force is moving and with initial velocity V will actually continue to move in the same direction. So it will continue to move with a constant speed along the line of the flux. So this statement is correct. Now it is given that period and the angular velocity are independent of the speed of radiance. So now let us see that if force is given as Q, V and B, for example, it is acting, there is a perpendicular component to it, so that sine theta will be 90 degree. So sine 90 will be equal to 1. So this will be QVB. And this force, this is the magnetic field, and this is the direction of motion of the particle, which is perpendicular to the direction of the magnetic field. So obviously the force will act and it will try to make this particle go round. So we say that this force will be equal to mv square by r, where v is the velocity and r is nothing but the radius of the circle. Radius. Okay. So 1v and 1v cancels out. So let us find velocity, which is equal to nothing but qb r upon m. But in the question, angular velocity has been asked. So angular velocity, we know the relation v is equal to omega into r. So from here, angular velocity omega can be given as velocity, linear velocity upon r, which is nothing but qbr upon m into r. So this r and r get cancelled out. So angular velocity is given as qb upon m. So angular velocity is independent of radius. There is no r term here. Now, what is the period? So time period t is given by omega is given as 2 pi by t. So t would be given as 2 pi upon omega. So now if omega is independent of r, that means time period is also independent of r. And if you replace the omega over here from here, you will get t is equal to 2 pi into m upon qb. So this is also independent of r. So this statement is also correct. So both the statements are correct. Also remember that if the velocity is having both the component like the horizontal as well as the vertical component, so in that case the path would be helix. That is, the particle will try to like go in a straight path, but force will be acting on it perpendicularly. So this path will be actually like this, and the velocity which is not perpendicular to the direction of the magnetic field will not experience any Lorentz force, and hence that velocity component, that is the horizontal component or the axial one, will be constant. This is the extra bit of information that you should remember. Now let's move to the question number 106, wherein it is said that the specimen, metal or a semiconductor carrying a current, is placed in a transverse magnetic field. An electric field is induced in the direction of I and perpendicular to B. This phenomenon is known as the Hall effect. So what is Hall effect? Say suppose this is Z axis, this is X and this is Y axis. So according to the Hall effect, if any specimen is kept in such a way that the magnetic field is along the Z axis, that is perpendicular to the specimen. Let's say current is going to either X axis or Y axis. Let's say suppose Y axis. So again here, what will happen? Since the current is nothing but flow of electrons, that is the charge particle, and when charge particle is moving in the transverse magnetic field, we have seen above that Lorentz force comes into picture. So this Lorentz force, if this is the specimen, and this Lorentz force will basically act on it and will try to push the electrons in the direction of the force. So suppose here. So there will be like charge develop in this region positive, and here there will be a diffusion of electrons because all the electrons have been pushed up. So here it will be negative, sorry, positive. So a potential difference known as the Hall voltage will develop, which is known as the VH. So VH is given by VI RH, where is the Hall constant upon omega, where this is nothing but omega. So in the question, it is saying that an electric field is induced in the direction. Electric field is not induced, a potential difference is created, and when the potential difference is created, then electric field is induced. But potential difference is created. Why the potential difference is created? Due to the Lorentz force. It is not that the Lorentz force generate electric field or something like that. Lorentz force creates the potential difference because it pushes the charge particles to upper edge. So this statement would be wrong. An electric field is not induced. Charge particles are being pushed due to which potential difference is induced. So the Hall effect can be used to determine whether the semiconductor is n-type, p-type, and to find the carrier concentration. This statement is correct. Why? Because the Hall effect, like the voltage, that is the potential difference that is created, if it is like positive, we say that it is a p-type. If it is a negative, we say that it is a n-type or metal. So yes, the Hall voltage can be used to determine whether the semiconductor is n-type or p-type. For p-type, it would be positive, and for n-type, it would be negative. So option 2 is correct. Now let us move to the next question, wherein it is asked about the tunnel diodes. So let us first see what is a tunnel diode. See, it is highly doped. Highly doped. Highly doped means the concentration. First of all, it is extrinsic, wherein impurities have been added to it, and the concentration of the impurities, that is in the p type and the n type, are very very high. And we know that the width of the depletion region is inversely proportional to the concentration of the impurities, either Nd or Na. What is the formula of width? 2 epsilon upon q, 1 upon Na plus 1 upon Nd into V naught root over, where V is the voltage across the diode. So we see that W is inversely proportional to Na and Nd, or the root over Na or Nd. Correct? So if Na and Nd is very highly doped, what we can say about W? The W is very small. And in case of tunnel diode, it is very small, and the depletion region is of the order of the wavelength of light. Wavelength of light in visible spectrum. Okay. So what will happen? Just remember few points. First of all, switching will be very fast. Switching will be very fast. If switching is very fast, then it will be used in those circuit where switching speed is required is very, very high. Very low latency is required. Also it can be used in an oscillator to produce very high frequency. Also, tunnel diodes is always operating. It is never in cutoff. Always operating, never in cutoff. Okay. So we can say that the V cut-in is almost zero. Cut-in voltage or V threshold voltage is zero for tunnel diode. So if you see the characteristics, this is the characteristics of the tunnel diode, where this is called the peak current IP, this is called the VP, this is the valley voltage VV, this is the valley current. So you see here the diode is acting as a positive resistance, slope is positive. In this region, that is the region between the peak and the valley, the diode is acting as a negative resistance. So you have to remember the region where the diode is acting as a positive resistance and a negative resistance. So before peak, it is acting as a positive resistor, and after peak, it is acting as a negative resistor. So in the question, it is asked the tunnel diode exhibit a positive resistance characteristics between IP and IV, peak and valley current. So between the peak and the valley current, it does not exhibit the positive resistance, rather it exhibits the negative resistance. So this statement is wrong. See, since tunneling takes place at a very high speed of light, the transient response is limited only by the total shunt capacitance, that is the junction plus tray wiring capacitance and peak driving current. So this option is correct. So option 2 would be the right answer. Again, a different type of diode is asked, which is the Schottky diode. So in the Schottky diode, in the diode, there are two types of capacitance. One is called the diffusion capacitance, which is given by CD is equal to tau into G. Another is called the transition capacitance or junction capacitance. So these two capacitance are formed in the PN junction. So in the Schottky diode is basically a type of diode in which there is either a p-type semiconductor with a metal or a n-type semiconductor with a metal. So it's a metal semiconductor type diode. It's a metal semiconductor type diode. Okay. So why we use metal semiconductor type diode? Because it makes CD0 and transition capacitance at very, very low. This is the one of the property of the Schottky diode or metal semiconductor type diode. Also, when we have n-type semiconductor mixed with the metal, we have the work function of the metal greater than the n-type semiconductor. And if we have p-type semiconductor plus metal, then work function of the metal will be less than the work function of p-type semiconductor. This is very important, just remember. So if n-type semiconductor and metal is used to form the Schottky diode, then we will say that the work function of the metal will be greater, and for p-type, the work function of the semiconductor will be greater than the metal. So in the question, it is said that the Schottky diode is one of the diode which have zero diffusion capacitance and smaller transition capacitance than the normal PN junction diode. So even if you do not know the exact exact functionalities of the Schottky diode, so from the normal, and you know that the Schottky diode is a metal semiconductor diode, so you can obviously mark this as correct as it is asking that the smaller diffusion capacity, smaller transition capacitance and zero diffusion capacitance with respect to the normal PN junction diode. Since a metal semiconductor having one end is metal, another end is semiconductor, so obviously this should be the correct. And we've also seen here. Then the Schottky diode is normally constructed by a metal, okay, and an N-type semiconductor in which the work function of the metal is smaller. It is not smaller, it is greater than that of the semiconductor. So this option is wrong. So option 1 is correct, only A. In the next question, we have been asked about the hybrid parameter of the transistor. So let us see what is the hybrid parameters. We have representation like this, V1, I2 in terms of hybrid parameter H11, I1 plus H12, V2, and I2 is equal to H21, I1 plus H22, V2. Just if you remember this, V1, I2, and here we have I1, and here we have V2, then you can figure out the different parameter values. For example, what would be H11? H11 will be nothing but V1 upon I1 given V2 equal to 0. So if we are asked about H11, we can say that it is nothing but voltage upon V upon I, that is nothing but R, resistance. And in transistor, this is known as HIE. Also remember as the input resistance Rn, and in high frequency we call this as R pi. Remember the terminology. HIE, H11 is known as the H11 is called as the HIE, R input or R pi. Similarly, if we talk about H12, we will say it is nothing but V1 upon V2 given I1 equal to 0, and V1 upon V2 is what? V1 upon V2 is reverse voltage gain. Voltage gain would be what? Output upon input, V2 upon V1. But V1 upon V2 is what? Reverse voltage gain. We'll say HR. So this is HR. H11 is HIE, that is the input resistance, and H12 is nothing but the reverse voltage gain, HR. Now let us go for H21 that has been asked from the question. So H21 would be nothing but I2 upon I1, and provided V2 equal to 0, and this is output current upon input current, so this is called current gain. Also remember, when V2 equal to 0, what we say? When voltage V2 equal to 0, we say that short circuit. Okay. When I2 equal to 0 or I1 equal to 0, input current is 0. That means the open circuit at the input end, short circuit at the output end. So this is nothing but the current gain, and this is also called as the HFE or beta for the transistor. So H21 is nothing but HFE or beta. So similarly, we have H22, which is nothing upon but I2 upon V2 given I1 equal to 0. If you put I1 equal to 0 in this equation, I1 equal to 0, this term will cancel out. I2 upon V2 will be H22. So I2 upon V2 is what? Transconductance, not resistance. So this is nothing but 1 upon HOE. That is 1 upon resistance. So in the question it is asked, and HOE is nothing but the output resistance. Okay. So in the question it is asked, H21 is input resistance with output short circuited. Input resistance means HIE, or we can say input resistance means what? V1 upon I1 with output short circuited, V2 equal to 0, and we have seen that this is nothing but H11. It is not H21. So this is not. Reverse open circuit voltage also amplification, we have seen that reverse HR. This is nothing but H12. Short circuit current gain, this is the correct answer. So now let us move to the next question, wherein it has discussed the CE, CB, and CC. That is common collector, common emitter, and common base. So just remember, when we say that a common emitter, it is mostly used. Why? Because it has the moderate input resistance and moderate output resistance. It is neither infinity nor zero, neither infinity, non-zero, a mid-level. That is the moderate. Whereas in common collector, what do you mean by the common collector? That means the collector is common, input is applied at base terminal and output is taken at emitter. This is the common collector. Collector is common to both input and output. So input you apply at the base and output you take at the emitter. So if this is a transistor and this is the collector input where you have given VCC, this is the base. So you provide input over here and obviously there will be an emitter resistance RE which is grounded. You take output over here. So this is the common collector. So in common collector what we have? See, output is taken from here. So output resistance R out is very small. On the other hand, input resistance is very high. If you figure out one of the resistance, that is input or output, the other will be reciprocal. Output resistance here is very small. Input resistance here is very high. And the common collector is also known as the emitter follower. It is also known as the emitter follower. So sometimes if it is not given that CE or CC, it is given as emitter follower. That is the output is following the emitter. That would be the correct. Okay. Now in common base, like in the common base, we have input very small and our output is very high. Okay. So just remember that common emitter, both the things are moderate. Input resistance, output resistance are of moderate. In common collector, that is, we have taken the output from the emitter. So our output is very small. Our input is very high. You can take it as infinity, this at zero. Common base, our input is very small, but our output is very high. Now let us move to the question wherein two statements are given. Statement 1 is current gain and input impedance in CE transistor configuration is usually higher than CB transistor configuration. So in common base, we have seen that the input resistance is very small. We can take it as 0. And output resistance is very high. That is taken as infinity. So this is basically and the current gain input impedance, common emitter transistor, we have seen it is moderate. It is neither 0 nor infinity, but a mid value between that is usually higher than CB. And CB input impedance is 0. So this is the correct statement. Because CE we have some finite values that is moderately high. And CB we are almost near to 0, very small. The output impedance in the CC configuration, common collector. So we have seen in the common collector, output is very low, is higher than the CE configuration. In CE, common emitter, the output impedance or input impedance is moderate. It is neither very high, that is up to infinity, or nor very less, that is 0. So here output impedance of CC is very small. So it is not higher but lower than the CE configuration. So this statement is wrong. So for 112, this answer 1 is option A is correct. So this is all with this EDC topic. Thank you.